So hello and very good afternoon. In this lecture of mine, I am going to discuss what is Bose-Einstein condensation with its brief history. So let us try to understand what bosons are at the very outset. To grasp Bose-Einstein condensation, we first need to understand what bosons are. In the world of quantum mechanics, particles are classified into two categories based on their spin: fermions and bosons. Fermions are particles with half integer spins like 1 half, 3 by 2, 5 by 2, etc. and obey the Pauli exclusion principle, meaning no two fermions can occupy the same quantum state simultaneously. Electrons, protons and neutrons are examples of fermions. Bosons, on the other hand, have integer spins like 0, 1, 2, 3, etc. Unlike fermions, bosons can occupy the same quantum state without restriction. This ability to share a quantum state is a key feature that makes Bose-Einstein condensation possible. Examples of bosons include photons, phonons, helium-4 atoms, and gluons. The concept of Bose-Einstein condensation traces its origin back to the early 20th century, when two genius minds, Satyendranath Bose and Albert Einstein, developed the theoretical framework for this phenomenon. The story begins with the Indian physicist Satyendranath Bose, who in 1924 made significant contributions to quantum mechanics. He developed statistical methods to describe photons, which are particles of light. Bose sent his work to Albert Einstein, who immediately recognized its importance. Building on Bose's work, Einstein extended the theory to atoms, predicting under certain conditions, and these conditions were extremely low temperature conditions, a large number of particles would occupy the same quantum state. This theoretical prediction is what we now know as Bose-Einstein condensation. However, at the time, this was purely theoretical. No one had observed such a state of matter. For many years, the Bose-Einstein condensate remained a theoretical curiosity. It wasn't until advancements in experimental techniques, particularly in cooling and trapping atoms, that scientists began to explore the possibility of creating Bose-Einstein condensate in the laboratory. The breakthrough came in 1995 for the first time when physicists Eric Cornell and Carl Wieman at the University of Colorado, along with Wolfgang Cutler at MIT, successfully created the first Bose-Einstein condensate using rubidium atoms. By cooling the atoms to just a few billionths of a degree above absolute zero, they observed the atoms collapsing into the same quantum ground state, confirming the existence of Bose-Einstein condensate. This achievement earned them the Nobel Prize in Physics in 2001. So we need to understand the quantum states and quantum levels. In quantum mechanics, particles like atoms or molecules exist in specific energy states or levels, often referred to as quantum states. These states are defined by parameters such as energy, position, momentum. At ordinary or higher temperatures, particles are spread out over a range of energy levels. They are constantly moving, jostling around, and occupying higher energy states due to thermal energy. This movement is why we see gases filling up containers, liquids flowing, and solids vibrating at the atomic level. As we start cooling the system, the energy of the particles decreases. Their movement slows down and they begin to occupy lower and lower energy states. However, in most everyday situations, particles still occupy a variety of energy states even at low temperatures. The role of temperature in Bose-Einstein condensate formation. Now let's talk about what happens when we cool bosons to extremely low temperatures, specifically to just above absolute zero, that is minus 273.15 degrees Celsius. Every particle has a wave-like nature described by its Debye wavelength. This wavelength is inversely proportional to the particle's momentum, meaning that as the temperature decreases and the particles slow down, the de Broglie wavelength increases. When the temperature gets low enough, the de Broglie wavelengths of the bosons become comparable to the distance between them. As the temperature continues to drop, these wavelengths start to overlap. When this happens, the individual wave functions of the particles, essentially the mathematical descriptions of their quantum states, merge together. At a specific critical temperature, something extraordinary happens. A large fraction of the bosons in the system all occupy the lowest quantum state, which is the ground state. Instead of behaving like individual particles, they begin to act as a single quantum entity with a collective wave function. This process of all the bosons collapsing into the same ground state is what we call Bose-Einstein condensation. It's like all the particles are singing in perfect harmony, moving in lockstep as if they were one giant particle. Once the bosons form a Bose-Einstein condensate, the system exhibits unique properties that are distinctly quantum mechanical. First of these unique properties is coherence. In the condensate, the wave functions of the individual bosons are coherent, meaning they are in phase with one another. The coherence is what gives the condensate its strange unified behavior. Then superfluidity. One of the most striking features of Bose-Einstein condensation is superfluidity, the ability of the condensate to flow without viscosity or resistance. Imagine pouring a liquid that doesn't slow down or gets stuck due to friction. That's what superfluidity is like. It's as if the fluid is perfectly smooth with no internal friction. Normally, quantum effects are observed only at very small scales, at the level of atoms or subatomic particles. However, in a Bose-Einstein condensate, these effects scale up to a macroscopic level, meaning they can be observed directly in a lab. This is why Bose-Einstein condensation is so remarkable. It's quantum mechanics brought into the visible world. Let's try to understand Bose-Einstein condensation with an example. Let's visualize this with an example. Imagine you have a room full of dancers, each dancing to their own rhythm, which represents particles at high temperature, each in their own quantum state. As the music slows down, which represents cooling, more dancers start to sync up with each other. Eventually, when the music is nearly silent, that is, the temperature is just above absolute zero, all the dancers move in perfect unison, performing the same dance. In Bose-Einstein condensation, this synchronized dance is the particles occupying the same quantum ground state. The creation of the first Bose-Einstein condensate in 1995 by Cornell Wieman and later Kettle allowed scientists to observe these quantum effects on a large scale. For example, interference patterns. When two Bose-Einstein condensates are allowed to overlap, they produce interference patterns similar to those created by overlapping light waves. This demonstrates the wave nature of matter at macroscopic scales. Then, vortex formation. In a rotating Bose-Einstein condensate, scientists observe quantized vortices, essentially little whirlpools where the entire condensate swirls around. These vortices are a direct result of the quantized angular momentum, another quantum mechanical property. Now, let's try to think why Bose-Einstein condensation is so revolutionary. Bose-Einstein condensation is more than just a new state of matter. It's a bridge between the classical and the quantum world. It provides a platform to study quantum mechanics in a tangible way, and it has opened up new avenues for research in areas like quantum computing, quantum simulations, and precision measurements. The fact that we can create and manipulate a Bose-Einstein condensate in the lab means we have a powerful tool to explore the foundations of physics itself. So now let's come to the conclusion. So the science behind Bose-Einstein condensation is a tale of how cooling bosons to near absolute zero unveils a world where quantum mechanics reigns supreme. At these ultra-cold temperatures, particles lose their individual identities and merge into a collective whole, showcasing the unity and coherence that defines this fascinating quantum state. Whether it's superfluidity, macroscopic quantum effects, or potential applications in technology, Bose-Einstein condensation continues to be a cornerstone of modern physics, challenging our understanding of the quantum world. Thank you.